Right, good morning again and welcome back. I had to finish in a bit of a rush yesterday, so let me just remind you where we'd got to. I had been considering the induction equation for a magnetic field B in a perfectly conducting fluid. And the equation is given by this, dB by dt is the curl of U cross B, sometimes written as the Lie derivative with respect to the flow U of the field B. Many of you may prefer this sort of notation. I cling to this notation. I've been using it for the last 60 years, and it's very difficult to change your ways, your habits of a lifetime. So notice immediately the similarity of structure between the magnetic induction equation in a perfectly conducting fluid and the vorticity equation derived as the curl of the Euler equation in an ideal inviscid fluid. Now that's an inviscid fluid without any magnetic effect whatsoever. It's just the traditional, the very, very old classical equation, as in effect considered by Helmholtz. Helmholtz proved on the basis of this sort of equation that the vortex lines are frozen in the fluid. The difference in a way between the two equations is this, that this one was discovered much later by, as I mentioned, Alfvén in 1942, that here B and U are really quite independent. We can, for quite arbitrary U, any velocity field in the conducting fluid, this is the way in which the magnetic field evolves. And of course you then want to derive from some dynamical equation, typically the Navier-Stokes equation, and we'll come to that later. But this equation here already contains the dynamics. It's not just any U. That U is related to omega. Omega is the curl of U. So whereas this equation is linear in B if U is prescribed, this equation is very definitely nonlinear. It's a nonlinear Euler equation. And of course, that is the great difficulty of the Euler equation and why it attracts so much attention. I mean, one of the clay problems is still related to this equation. Does the, under this evolution for given initial conditions, does the solution remain regular, smooth for all time? And we don't know the answer to that. Half the world thinks yes, and the other half thinks no. If you go to a conference of experts on this topic and ask for a vote, that's roughly the way it divides. The clay problem was actually phrased in terms of the Navier-Stokes equation, not the Euler equation. So you have the extra diffusion term here, plus nu del squared Laplacian of omega. And the question is, does that remain regular for all time? And that's one of the clay millennium problems as yet unsolved. So as I say, we have, and I proved last time, that the helicity of the field B, defined as the integral of A dot B over a Lagrangian volume, a volume that is moving with the flow U, that is a constant. dH by dt was 0. It's a constant of this linear induction equation. But it's a constant that follows simply because the B lines are frozen in the fluid. And if you realize that it's topological in that sense, it's related to the conserved topology, then immediately there must be a similar invariant for the vorticity equation, even although it's a nonlinear equation. And that's the beauty of it, really, that it's because the omega is frozen in the fluid, a particular flow related to that omega, but nevertheless it's frozen in the fluid in that flow. Therefore, this helicity is a constant. Now, it's the analogous helicity I've called H of defined in terms of omega. So we take the omega here, the analog of B, and U, the uncurl, if you like, of omega, the analog of A. So think of U here as the vector potential of the vorticity field. And that is the helicity, the kinetic helicity associated with the Euler equation, and it is a constant. And the proof of that, you can go step by step. Take the proof that I gave you last time on the board here for dH by dt equals 0, and it applies equally at every step to proving that this rate of change of this quantity is equal to 0. And the point is that in the course of that proof, you actually make no use of the fact that omega is the curl of u. It doesn't matter. We could take any other velocity here. It doesn't have to be the uncurl of any other velocity here. And this integral would still remain invariant. Anyway, so that is the invariant helicity. Now, the interpretation of that helicity I did include in the notes, which you may have been able to look at on the web. But if you have two linked vortex tubes, let me draw them like this, the simplest possible linked topology, so like this, we have to define a flux, call it phi 1. That's the integral of the magnetic field across this. Now, it may be, for example, a Gaussian, a nice smooth profile of vorticity, or of magnetic field, whichever context, it's the same now. And here we have a different, I've taken that this way, so let me, well, I'll take phi 2. I think I've taken a left-handed linkage there. So the helicity invariant, h of b, can be worked out very simply for this configuration, particularly if you assume that the cross-section of both of these flux tubes is very small. It's the simplest way to think about it. If you take then the integral of a dot b, then integrating across one of the tubes, you get a b across the tube gives you the phi, which then comes out of the integral. Phi 1 times then a line integral round the tube of a dot dx, and that's the other flux, phi 2. So you get phi 1, phi 2 when you go around one of the tubes, and you get another phi 1, phi 2 when you go around the other tube. So you get 2 phi 1, phi 2. That's if they're linked. And I'll put a plus or minus here because it's plus if it's a right-handed linkage and it's minus if it's a left-handed linkage. And I'll put an n in here, an integer, because after all I gave you the simplest link, but I might have taken one that goes round several times before it joins up. It could go around 3, 4, any number of times, and that's the n. It's the Gauss linking number of the two central curves of these vortex or magnetic flux tubes. So that is what, in a way, relates this invariant that you derive from the equations of magnetohydrodynamics and the fundamental invariant, n, the Gauss linking number of the two tubes. So there's the bridge established between fluid mechanics, if you like, and now if it's vorticity, if it's this integral you're considering, similarly invariant, then instead of magnetic flux, you have vorticity flux, which is usually described as the circulation around each of the two tubes, flux of vorticity. And that is conserved. It's the sort of thing, in a way, that Kelvin must have been looking for, but he didn't find, because somehow it's much more difficult to find it for if you just start from the Euler equations without any knowledge of this sort of thing for the induction equation, because you're starting with a nonlinear problem, and at the outset you don't think it's going to be possible to find new invariants for a nonlinear problem of this kind. But it is the invariant, and we have to cling to that and make the most of it. Well, now, what if it's a knot rather than a link? So this is what you're mostly concerned with, something like this, a trefoil or any more complicated knot. What is the expression for the helicity? Now, this is a more difficult problem, and it's easy to to get it wrong, but I'll tell you the answer. And this is something that, so let's call it for a knot, is equal to, it looks like this. It looks like the plus or minus 2n phi 1 phi 2, but you've only got one flux in this case, the flux of the field through the, in the knotted tube. So what can it be? Well, it's got to be phi squared on dimensional grounds, so we'll have a coefficient, h times phi squared. And the question is, well, what is h? Well, h is our old friend, Reith plus twist. Reith plus twist. And therefore, again, the fact that we know this is conserved, it's an invariant, a fundamental invariant, and flux phi is a fundamental invariant, that goes back to Helmholtz. Therefore, h is an invariant, and we know Reith plus twist is invariant, so everything hangs together nicely. And actually, the proof that Reith plus twist is invariant is, if you do it from differential geometry, I don't know if you know, you've got to take not just a closed knotted curve, C, but you've got to consider a ribbon of small width, of which C is one boundary, and C prime the other boundary. And you've got to consider the nature of the twist of the ribbon as you go around. You can't think about the twist of a curve, but you can think about the twist of a ribbon, of course. And if you have a ribbon, it's a bit like a flux tube. You take any two lines, the central line of the flux tube, well, if we're in a knot here, I take the boundary and call that the curve C, and take the another line of the flux tube, another B line, and call that C prime, and think of these as the boundaries of a ribbon going right round the tube. Now, the ribbon will be closed only if the B lines are closed. And that's not, it's not certain for any flux tube. It is for a ribbon. You can change the twist of a ribbon by Den surgery. Take your closed ribbon in a knot. I can cut the ribbon and twist it through 2 pi and join it together again. And the twist will have changed by an integer, in fact, in that process. So how has that got to be represented? Well, it does appear through the twist here. There are formulae for Reith and twist. The Reith is 1 over 4 pi times the double integral going around C both times dx, well, I make it x minus x prime dx cross dx prime over x minus x prime cubed. A Gauss type integral. This would be for linking, or link, if you had C1 and C2, it is the Gauss integral, the linking number, which is invariant. But that Reith integrating twice around the same curve is not an invariant. It varies continuously as you deform the curve. Not invariant. That's why you need the twist as well. So it's not, and I mean NOT, not KNOT this time, not invariant. Invariant. It doesn't, it looks as if it's not even convergent, but it is a convergent integral. Looks as if it has this nasty factor on the bottom, cubed. But the apparent singularity there, when x equals x prime, because you're going around the same curve twice, is cancelled nicely by, partly by this and partly just by the triple scalar product when you really look at the detail. It is a nicely convergent integral that varies continuously as you deform the curve. You can see why it's got to vary, because, I mean, the standard thing, if I take a single circle, then the Reith is 0. But if I go through one of these Reidemaster moves, so we pull it and twist it through 2 pi, then we get a Reith here that is plus or minus 1. And here the Reith was 0. And the Reith, as you've gone through this deformation, has varied continuously between 0 and plus or minus 1. So it's certainly not invariant. But that's compensated by a change of twist. And the twist here, well, do we have a formula for that? There are two parts to it. One part involves the torsion, and it's 1 over 2 pi times a single integral round the curve of the torsion. I'll call it d, s being arc length along the curve. So torsion on the curve, the manner of twisting out of the plane, is what appears here. So that's one part of the twist. But then because we can do this den surgery, cutting and twisting, we know we can change it by an integer. So I have to put on here plus n. And this is an integer for a ribbon. That's when, like the situation of a flux tube, when all the magnetic field lines going around the tube are closed curves. As I say, that's a little special, because after all, you could cut a flux tube and twist it through an angle that's not 2 pi and then join it together. And then if it's irrational, then the magnetic field lines would go round and round forever and never close on themselves. So there are subtleties there. But that n is an integer. Now, so what happens, you see, with the twisting and deforming business? In fact, what happens as you go through here? And I like to illustrate this. It's what Zeldovich, I remember, I saw him doing it first. He took the belt off his trousers and he had difficulty then holding them up. But you take one of these, you see now, well, I guess if I twist it through 2 pi and go like that. Now there, it doesn't look twisted, but you see a Reith. Reith is equal to 1, or maybe it's minus 1. Let's not worry about the sign too much. Now, we imagine this is part of a large circle, but this little bit, we simply deform. We deform continuously. And the Reith has, contribution to Reith has disappeared, but we've got a 2 pi twist. So the question is, just when does that happen? How does it happen? Because I think of a vector transverse to this ribbon in the direction of these 2 index fingers. Going around the curve at this point, that index finger wouldn't rotate at all. It's got to, since the 2 fingers are parallel, it's got to rotate by an integer number. And when I've got out to here, the total rotation is 1, a unit rotation. So it's an integer all the time. Here it's 0. It's pretty continuous deformation. And here it's 1. So something funny has happened. How can that be? All right, a continuous variable that jumps. Well, it's not allowed. That's a good one, isn't it? We should have that in the, pose that in the tutorial. Explain this phenomenon. Well, I will tell you, it happens, and you might be able to analyze this. Renzo and I did analyze it and explained it all in 1990 something in a paper in the Proceedings of the Royal Society. It happens, this deformation, at a certain point, the curve, the centerline curve or the either boundary, has to pass through an inflection point. That's an inflection point where the curvature is 0. And when the curvature is 0, the torsion is infinite. But it's infinite in such a way that it's an integrable infinity. But the integral of the torsion jumps at that stage by an integer as you go through the inflection point. And there's a compensating jump in this integer here that just keeps the twist continuous. All right? Because the Reith varies continuously, twist plus writhe is invariant, therefore twist, TW, must vary continuously as well. But it consists of two parts that that are discontinuous as you go through the inflection point. That's very curious. And to analyze that behavior near the inflection, well, obviously you've got to take a local analysis. This is the Reidemeister move, isn't it? His first move. So it's very, very basic. One should understand what is going on at this critical instant. Okay, well, I am in these notes that I've taken so much care to produce, I'm going to have to skip an awful lot of it. In particular, I just mentioned yesterday that helicity is terribly important in dynamo theory, because if you have a large expanse of fluid and in turbulent motion with non-zero helicity, so non-zero entanglement of the vortex lines, non-trivial entanglement, then a magnetic field will grow generically on a large scale. Well, I'm not going to go into that theory because your interest is more in knots. And so I'm going to jump to the next main section, which still involves helicity in a very important way, which I'll just explain in a moment. But I'm going to be concerned with the process of relaxation under the topological constraint of, particularly of conserved field topology, which includes conserved invariant helicity. Now there is an important inequality, and I'll just put it here. I'll call this the Arnold inequality. Inequality. Because I think Arnold actually recognized this for the first time in 1974 in a most inaccessible paper. Completely inaccessible. You'll never find this paper. It was in the proceedings of a conference on differential equations held in Yerevan in Armenia. And the proceedings were published in Russian, of course. This was the old Soviet Union, but they never found their way to the West at all. However, Arnold was kind enough, when the subject suddenly came to life again in the 80s, to have this paper republished in English in 1986 in a journal called Selnik, the selection of Russian papers translated into English for the benefit of Western readers, edited, I think, by Arnold himself. He was very keen that these old papers from the Russian literature should become available in the West. I think Arnold always felt that insufficient credit was given to the Russian. That's probably true, just because of the great barriers that existed at that time. Anyway, Arnold's inequality, what is it? Well, it is an inequality for magnetic energy. If I define magnetic energy, half the integral throughout some domain of fluid, b squared dv, it's that energy that's going to play an important part when we think of a knotted flux tube. It's a very natural definition of the energy of that knot. And it's sort of an energy you would use if you're approaching this, as I am, from a very physical point of view. The inequality is that m of t has a lower bound. So it's greater than or equal to a certain constant, which is usually written as q0 to the minus 2 times the modulus of the helicity. The helicity, that's the helicity of the field B, which is conserved under any deformation. So this is a fixed constant. And that is the lower bound of the magnetic energy. You can't go less than that. And that is very simple to prove. It's based on just a Schwarz inequality. Schwarz inequality that tells you that, firstly, H is less than or equal to, you've got an integral of b squared times an integral of a squared. Remember, this is a dot b essentially, so that to the power of half. That's the first. This is Schwarz. And there's a Poincaré inequality, which you get by minimizing the integral of b squared over the integral of a squared. The integral of curl a squared over the integral of a squared. By the calculus of variations, you can find the minimum value. It's the Rayleigh quotient. The minimum value of that is what is less than or equal to the 1 over q0 squared. q0, you've got a domain. Then q0 is something like, it's a length. And it's a length determined by the geometry and the size of the domain. And this comes out, calculus of variations, you know how you take this quotient and use Lagrange multiplier and minimize and so on. You end up with a Helmholtz problem, an eigenvalue problem, and the q0 emerges as the eigenvalue of that problem. So combining these two, squaring this one maybe and multiplying the two together to get rid of the a squared, you get an integral b squared alone, and that is what leads round to this. Combining the two, you get this Arnold inequality. So the magnetic energy has a lower bound. Okay, now I can go to these pictures, and I show you here a picture of Brian Taylor, who's been very much involved in the business of magnetic relaxation in the fusion context. He was the director of the Cullum Laboratories in Cambridge, in Cambridge near Oxford, for many years, and still going strong. I'll show you a little picture of Cambridge here. This is where we practice our experimental fluid dynamics. And this was a nice picture of a helical shrub growing in Aix-en-Provence, which I took a year or two ago. Okay, well, many physical systems, as you know, have a natural tendency to minimize their energy, subject to any topological constraints that may apply. So, for example, if we take this figure of 8 knot, which comes nicely from Sharain's knot plot, it's a flexible wire, and you release it. Actually, I took it in this form and suspended it on a thread, which you don't see from the ceiling, and let it relax, and this is what it relaxes to. It comes into contact with itself at 2 points. So the 4 crossings now look like 2, but there are 2 that more or less coincide here, and 2 others coincide here where the crossings occur. So that's, if you like, elastic relaxation. A stiff wire, in the form of a figure of 8, springs to a minimum energy equilibrium when released from a constraining envelope. This is the way it comes. In this equilibrium, the wire makes contact with itself. The 4 crossings now occurring as 2 double crossings. This is when, you might say, the topological constraint, the fact that it is knotted, it bites, it takes effect. And that is a minimum energy configuration, and it would be nice to actually calculate that geometric shape, but you'd need to be given the elastic stress-strain relationship and whatnot for this wire. Nice problem. Okay, now magnetic relaxation is rather similar. Under topological, it's a means of determining magnetostatic equilibria, that's the ultimate equilibrium, which will be a minimum energy state, but with prescribed topology, like the topology of that wire. And the useful model is a perfectly conducting but viscous, incompressible fluid. Perfectly conducting so that the topology is conserved, viscous so that we can dissipate energy. and incompressible just because it's easier to think about volume preserving deformations. And we take an arbitrary initial magnetic field, B0, x, t, released in a fluid at time t equals 0, but the fluid initially at rest. Okay, so we think of this, it's a thought problem. Magnetic field, it could be in the form of a knot, one knotted flux tube. That's the way you like to think of these things, or any link. Okay, fluid at rest, and we just release it and let it go. What happens? Well, the Lorentz force, that's J cross B, J being curl of B, J cross B, force in the fluid, and generally, initially, that is rotational. The curl of that is non-zero, so it can't be balanced by just a simple pressure gradient. The fluid has got to move. The fluid moves in response to that Lorentz force. Now here I've called it V, the velocity field. Div V equals 0, volume preserving. The B lines are frozen in the fluid, energy is dissipated. But magnetic energy, here I've called it E for some reason, but I'm calling it M over here. Its energy is bounded below by this sort of thing. E greater than H over L, where H is the conserved helicity and L is some fixed constant. So we get that lower bound. So, okay, we're going to have a decreasing energy because of viscosity, but a lower bound. So it's got to drive it to a steady state. So magnetostatic equilibrium is attained. By magnetostatic we mean the velocity v will eventually go to 0 again. It starts from 0, it'll rise from 0, but it'll go back to 0. Now, the only thing to note is that tangential discontinuities of B, which are actually current sheets, can and in general do appear during the relaxation process. And that's best recognized in the relaxation of linked or knotted or braided flux tubes. Parker, the astrophysicist in Chicago, also has written a whole book about this business of the spontaneous appearance of current sheets in magnetic fields, and it all does depend on this sort of relaxation process. So, for example, if you think of the relaxation of a trefoil flux tube, simplest example, what happens is it's a little bit like the elastic problem. In a magnetic field, you have what's called Maxwell stress, partly tension in the tube, which is going to try and make it contract like an elastic band, and partly pressure, magnetic pressure, which is balanced by fluid pressure, so we can ignore it. And so this tube tends to contract, but it's a tube with a finite cross-section, and the volume is conserved because its div velocity is 0. It's an incompressible flow. So volume preserving. So as the length contracts, the cross-section must expand. And so we go to a situation like this, obviously. At some stage, the tube is, as it were, going to come in contact with itself. And that's where the current sheets appear. So it's just like the elastic wire. It comes in contact with itself, but in a rather more symmetrical manner, as I've indicated here. But what is conserved during this relaxation, the flux is conserved, and also the volume of the tube. These are the conserved quantities. Now you might start with the same knot in a slightly different configuration. This is still the torus knot actually, but it's in the form, if that was T23 or K23, this is K32. And that could well relax, and does, we believe, relax to a different equilibrium. So the equilibrium, the resulting equilibrium, is not unique. It may depend on the initial geometrical configuration of the knot. So the helicity, remember it's h phi squared, is conserved, and the magnetic energy, minimum magnetic energy, well now, what can it be? Here, on dimensional grounds, the two things that are conserved are the flux phi and the volume v, and nothing else so far as we know. The dimensions of energy are phi squared divided by length, so volume to the minus 1/3. And then we can have a coefficient here, which is dimensionless and depends on the knot. But it depends also on the amount of twist, h. It depends on the helicity. And remember that h is what I had over here somewhere. H is Reith plus twist. And that twist involves both the torsion and the internal twist of the magnetic field inside the flux tube. And that's something that is not met when you approach this in terms of ideal knot theory, where you simply take a knot and you build a tube around the knot and expand the tube until it makes contact with itself. And then you ask, what's the minimum length of tube? What's the geometrical configuration that will minimize the ultimate length of the tube? That's the way ideal knots are constructed. But that says nothing about the possibility of internal twist. The internal twist appears here very naturally because to define magnetic field, you've got to prescribe that. So there is a twist internally in this tube, and the coefficient, little h here, is a dimensionless number. It's a pure number which can jump by plus or minus 1, as I say, when you go through inflection points. So this can be a function, a dimensionless function of the dimensionless number. And this function here is interesting. We should focus on that because m, a function of h, it's going to be different for every knot. But anyway, if you give me the knot, then that's a function determined by the knot. Now, because it's not unique, there may be a spectrum of, in other words, a whole sequence of functions, m1 of h, m2 of h, m3 of h, corresponding to all the different equilibria. But there'll be one of them that gives an absolute minimum, the least m of h. And that really is what one is most interested in. It would be the simplest configuration, probably this one for the trefoil, rather than this one, which is a little more complicated. Obviously exhibits more crossings. Okay. I should say here the precise way in which the discontinuities form and what happens after they form is not well understood. They form because in the fluid context they have to squeeze out fluid when two surfaces actually come together. There is a sort of asymptotic behavior there. And then when they really do come together, in real life, diffusion cannot be neglected when you have a tangential discontinuity. And there are things called resistive instabilities that were discussed as early, well, way back in the famous paper of Furth, Kalin, and Rosenbluth. Yes. No, it's not. No, that's just a lower bound, and the minimum might be quite a bit above that lower bound. In fact, that you have equality there, only in a very special circumstance. You've got to have equality in both the Schwarz relation, which means that B has to be parallel to A. And I think in Poincaré it's, well, there you can get equality. But basically, if B is parallel to A, it's what's called force-free, special force-free magnetic field, very special structure. And that's very unlikely to be attained here because the pressure does remain important in the limit. So that just helps. That just gives you the confidence. Oh, and I should have mentioned here. You might think this lower bound is going to. You have this lower bound only if the helicity is non-zero. That's the proof of Arnold's thing. You might have a field. Suppose I take the Borromean rings. Nice structure. 3 flux tubes. No 2 of them are linked. If I take any 2 out of the Borromean rings, they're unlinked, and so the contribution to helicity is 0. And since that's the same for any pair of the 3, the total helicity of the Borromean rings is 0. Nevertheless, it's obviously a non-trivial topology. The Borromean rings are linked. It's a triple linkage. And it's very difficult to construct an invariant like helicity that distinguishes the Borromean rings from the unlinked triple. But nevertheless, there is a proof that the energy has a lower bound for any non-trivial topology, even if the helicity is 0. And that proof was given by Michael Friedman in 1988. Friedman is the Fields Medalist. He got the Fields Medal for his work on the Poincaré conjecture. But when he turned his attention to this problem, he managed to prove that magnetic energy does indeed have a lower bound for a non-trivial. Now, what did he mean by non-trivial field topology? It means that if you have a magnetic field and there is some closed line of force, if it's trivial, then you can contract the line of force to a point without any difficulty in the domain that you're concerned with. But if it's non-trivial, in contracting it to a point, you trap some other field lines, and you can't go all the way to a point without somehow, these other field lines being stretched to accommodate the contraction. And it's based on that sort of idea that Friedman proved that the magnetic energy has a lower bound if the topology is non-trivial in that sense. So we do have the lower bound, and then we do have the process that forces us towards an equilibrium. Okay, this is actually just a very simple example of relaxation, which the topology is trivial in a sense. It's a one-dimensional relaxation, but one can conceive of this. A field that has only one component at an initial instant, a sine wave. But this has to be not an incompressible fluid, but the opposite limit of what we call a pressureless plasma. A plasma, a conducting fluid in which is so tenuous, so low density that the pressure, fluid pressure, plays no part at all. Magnetic pressure is what matters. And if you have a magnetic field with this shape, then magnetic pressure is maximum here, 0 here, maximum again here, B squared. So what happens? The fluid wants to flow down the pressure gradient towards this point here from both sides. And I guess I don't know if this will work. I think there's a little movie there that ought to work. Maybe I have to press this to capture it. No. Oh, here we go. I didn't test this out. There, you see how it happens? It happened rather quickly. Watch it again. This is actual real relaxation based on a viscous fluid with 0 pressure. There's the sine wave that we start with, and there is the relaxed state. So it does really move quite rapidly and forms a discontinuity. It's a near we stopped before the discontinuity for obvious reasons, but a discontinuity forms at the null of the field. Now, if I go again after the initial rapid relaxation, well, yes, as I say, something else happens. After a discontinuity forms, diffusion kicks in a real fluid, and I think that shows up here. If I, yeah, it goes on evolving slowly. The plateaus decay to zero through diffusive processes that occur here. That dashed line is actually the velocity field, and solid line is the magnetic field. So we can do this sort of thing without difficulty in one dimension. And we can even go as far as 2 dimensions, but going to 3 dimensions to do numerical procedures of this kind becomes very difficult computationally. To conserve field topology during a relaxation process is not a straightforward matter. However, let's go on. That's a more complex initial condition, and there I think you can see a more interesting evolution that includes a little bit of diffusion to help things along. And one of the interesting things about this problem actually is that because of the relaxation, the zero pressure, the density field does, although we're neglecting pressure, fluid pressure effects, the density of the fluid builds up at the null points of the field in a very dramatic manner. The fluid flows towards the null regions, and you get very, very intermittent structure that appears in the fluid as a result of this sort of process. Well, then I come back to the 3-dimensional situation, and so just to resume and repeat in a way what I've already said. If you have a knotted tube, it's the flux integrated across the tube which is prescribed, if you like. It's immersed in incompressible, perfectly conducting but viscous fluid. The current is this, and the Lorentz force, F, is this. And in general, the curl of that Lorentz force is 0, and that's why the fluid flows and dissipates energy via viscosity. The field is transported. V, phi, and the knot topology, K, are conserved in this process. So the evolution is governed by the MHD equations, including this one here, and also the equation of motion, which is Navier-Stokes. The energy decreases subject to the constraint of conserved topology. As t tends to infinity, the system approaches equilibrium, for which J cross B is grad P. In other words, this Lorentz force is balanced by pressure in the final state. So although the curl of the Lorentz force is non-zero initially, it's got to become 0 ultimately. The magnetic energy at this stage is minimized. So you get to this state of affairs. Minimum energy determined by V and phi, so on dimensional grounds, M minimum is M phi squared V to the minus 1/3. M is a dimensionless number determined solely by the knot type K. But more generally, we have to allow for twist of B along the tube involving magnetic helicity. That helicity is H phi squared. H is twist plus Reith. And now the minimum can depend on H through this coefficient here. So that's what I've said already. And there is the picture. And this is the relaxation of the trefoil knot, which we studied with my student Atta Chui in 1995. And in fact, we were able to compute this function M of H for torus knots. And this is the torus knot. I don't know if it's legible at the back, but this is T23, T23, T25, T27, and T29. And so you see a gradual evolution. And there is an absolute minimum. Now, this is 40 on a scale here, and the minimum is around, I don't know, you can see where these minima are located. And they're not located at H equals 0. They're off 0 because these knots are chiral. There you have either a right-handed or a left-handed torus knot. If I think this is the right-handed torus knot, left-handed torus knot, we'd simply have to flip these diagrams in the axis H equals 0. Incidentally, the helicity, the minimum energy of the torus knot and its mirror image is the same, but the helicity changes sign. The H parameter, which is another feature, you might say, of a knot, an invariant feature, the H parameter, it changes sign as you go from the mirror to its image. So in that sense, you can distinguish through that type of invariant, you can distinguish one knot from its mirror image. Let's see what else I have here. There's a second analogy. I drew your attention to the analogy here between U and A, and therefore between the curl of U, which is omega, and the curl of A, which is B. That's one analogy, but there's quite a different analogy that we can appeal to now. And that is an analogy between, well, if you look at this equation for magnetostatic equilibrium, you can compare that with this equation, which is derived from the steady Euler equation. If I take this equation and think of a steady situation to which we relax, so d omega by t is 0, and uncurl this, then u cross omega is the gradient of a scalar, h. Don't confuse that one, I'm sorry, with Helicity h. It's a different one. So anyway, it's the gradient of a scalar, and that is unfortunately the usual notation. Well, so we have an analogy here, but be careful because the analogy is between u and b. So u and b, and the curl of u, which is omega, the curl of b, which is j. The change of order means that the analogy is between p and not h, but minus h. Okay? It's an analogy that's quite distinct from this one, and so you need great care in the interpretation of these analyses, of these analogies. But what it means is we have a result. We start with an arbitrary B, any topology you like, any knots, any links. Let it relax to minimum energy state. The topology is conserved, although discontinuities may appear. As always, that got to be added as a reminder. But you relax to an equilibrium minimum energy state, which is very relevant for knot energy. The analogy here is that if we start with an, well, it's just the end state that is analogous. Given a velocity field of arbitrary topology in a domain, there exists a steady solution of the Euler equations for which the velocity has the same topology as velocity, not vorticity. The streamline topology of the Euler flow is as given by arbitrarily. Okay? But to prove that, you have to go via the magnetic relaxation procedure involving this equation. It's extremely artificial to try and do it directly without appeal to magnetohydrodynamics. Well, I'll say a little bit more. I think I should stop there. If there are any questions on what I've said.